Good morning, good afternoon, and good evening, everyone, and welcome to this webinar titled Evidence Synthesis for Sparse Evidence Base, Heterogeneous Studies, and Disconnected Networks. I'm Sydney Menson from the events team here at Scientist.com, and I'll be your host for today. This webinar has been sponsored by ICON, so a big thanks to them for helping to make this webinar possible. We're very fortunate to have 3 speakers joining us today. First up, we have Dr. Katrine Heusler, a senior health economist in global HEOR and epidemiology at ICON, who mainly works in evidence synthesis, conducting analyses in both Bayesian and frequentist settings. We also have Dr. Matthias Hunger, lead epidemiologist, also in global HEOR and epidemiology at ICON, who is involved in all statistical components of research projects, including study design, protocol development, and data analysis. The last speaker with us is Dr. Nathan Green, a senior research fellow in the Department of Statistical Science at University College London. Nathan has many years of experience working on a wide range of projects across government and academia in defense and health. But just before we get started here, a few housekeeping notes. First, if the panels on your screen are too big or too small, you can zoom in or out in your internet browser to adjust their size. Next up, the webinar is being recorded and the video and its associated resources will be available to watch shortly afterwards. We'd love to hear from you and invite you to share any questions, thoughts, or comments in the Ask a Question box shaking on your screen. We will be taking your questions in a Q&A session after the presentation. If you'd like to learn more about what is being presented today, explore the resources panel where we've added a few relevant links and downloads. And finally, if you happen to have a technical issue, refreshing the page will nearly always fix things. But if it doesn't, reach out to us using the Ask a Question box and we'll help you to troubleshoot. And with that, I'd like to welcome our first presenter, Katrine. Thank you so much for being here today. Please take it away whenever you're ready.
Thank you very much, Sydney, for the introduction. Hello, everyone. So today we will give the webinar on evidence synthesis for sparse evidence base and other non-standard situations in evidence synthesis. So the presentation is structured as follows. First, we will give a brief introduction into evidence synthesis. Then we will talk about heterogeneity. Then we will show a case study on choosing suitable priors if the evidence base is sparse. We will then speak about matching adjusted indirect comparison, short MAIC, followed by multi-level network meta-regression, ML-NMR. We will then continue with the presentation. First, I will give a brief introduction into evidence synthesis. So what is that even? It just means that basically we pool all relevant randomized controlled trials, RCTs, of high quality in a specific medical field, which we have identified through a systematic literature review. And so by pooling, I just mean we put them all together, and there are specific statistical methods which can be used to do that. To calculate a pooled treatment effect, which could, for example, be a relative effect, such as an odds ratio or a relative risk, or also an absolute effect, such as a risk difference. And once we have estimated this pooled treatment effect, this can help us to draw conclusions on comparative efficacy and safety of the interventions of interest. So the main objective of evidence synthesis is that one RCT alone usually doesn't provide enough evidence to come to a final conclusion, which is the most effective and the safest treatment. As you probably all know from practical experience, RCTs often result in contradictory conclusions. So then sometimes we don't know which RCT we can rely on. Basically, a quality assessment can of course help to see if there are major flaws in the RCTs, which is also necessary when we do evidence synthesis, but it mainly helps like if we have contradictory findings then to come to a final conclusion. So that is one reason to conduct evidence synthesis. Another important reason is if we don't have head-to-head studies available. But even if we do have head-to-head studies available, we can do evidence synthesis, for example, pairwise meta-analysis, which is the simplest approach, and probably most of you are familiar with that, as we have seen in the poll already. So if we have studies directly comparing treatment A and B, we can then do a pairwise meta-analysis of all of these studies, and the weights are assigned to the individual studies based on the variance. If we do not have head-to-head studies available, we would then need more complex statistical approaches for comparisons, since also indirect comparisons are involved, as you can see in the graph at the right. If we have studies comparing treatment B to placebo and treatment A to placebo, but no studies comparing treatment A and B directly, we would then use a method for the indirect comparison. So there are both frequentist and Bayesian methods are available, such as the frequentist Bucher method or network meta-analysis, which exists both in a Bayesian and frequentist context. Both approaches have their pros and cons, so we cannot really say one is better than the other. It depends on many aspects, what is preferred. In a Bayesian approach, we have a prior distribution, which is formally combined with the likelihood to obtain the posterior distribution, and every parameter is defined as a random variable. We do not conduct any hypothesis testing, therefore we can say that one treatment is comparable to another treatment, and we do not speak of statistical significance, but we would then, for example, say one treatment is favorable over the other. We get results in terms of 95% credible intervals instead of confidence intervals, and these can be interpreted more intuitively, since Bayesian statistics is not based on repeated experimentation as classical statistics. We can interpret the credible interval as with 95% probability, a certain value lies within the interval. One major advantage of Bayesian approaches is that we can additionally incorporate information directly into the priors to strengthen the evidence base, which is especially relevant if we have a sparse evidence base. We can rank the treatments through the surface under the cumulative ranking curve, the so-called SUCRA. And we can also estimate probabilities of each treatment to be better than each comparator, which is not possible in a frequentist approach. The Bayesian approach is described in detail in the NICE Decision Support Unit guidelines, which gives both details on methodology and detailed examples, also with code in Winbugs or OpenBugs. Then a frequentist approach is basically a classical statistical approach, which is based on repeated experimentation. We conduct hypothesis testing, and therefore we can say that we can see a statistically significant difference or the absence of a statistically significant difference. The interpretation of the confidence interval is not as intuitive as the interpretation of the credible interval. If we have a 95% confidence interval, we would say that this contains the true population parameter 95% of the time. It's not possible to include any additional information into a frequentist NMA model in contrast to the Bayesian model, but ranking is also possible through the so-called p-score, which is a frequentist equivalent to the SUCRA. And so it can either based on weighted regression models, for example, following Rücker, or through the Bucher method, which is based on simple equations. Heterogeneity is also an important thing to consider when we do evidence synthesis. It is always present just by the nature that studies pooled always have some kind of variability, but some level is to be expected and tolerable. It just induces issue if the amount of heterogeneity is too extreme. And so we distinguish 3 types of heterogeneity. Clinical heterogeneity would be variability in participants, interventions, and outcomes. For example, if we have studies with a very old population and with a very young population we want to pool. Methodological heterogeneity is variability in study design and risk of bias. For example, if we want to compare crossover studies with RCTs. And statistical heterogeneity would be variability in the intervention effects as a consequence of clinical and or methodological heterogeneity. So we measure usually the amount of heterogeneity and then we account for it. There are certain ways to account for it, which I will talk about as well. So there are several assumptions which have to hold in a network meta-analysis. One key assumption is the similarity assumption. This means that one would expect the relative effect of A versus placebo to remain unchanged if the study was conducted under the conditions of B versus placebo and vice versa. So it means that the pairs of trials analyzed are comparable regarding potential effect modifiers. For example, the age distribution over the trials should be comparable if age is deemed a treatment effect modifier in a certain disease area. Here you can see an example for effect modifying. So there are 2 meta-analyses comparing treatment B and A and C and A, and these reveal that the treatment effect of B versus A is larger than the treatment effect of C versus A. However, this is caused by an imbalance in the terms of disease severity between the 2 pairs of trials. In the B versus A trial, there were 30% of patients with severe disease and 70% with moderate disease. And in the C versus A trials, the situation was reversed. So if the disease severity has an impact on the treatment outcomes in this indication, then this would induce a bias in the indirect treatment comparison. Before we can even start conducting our NMA, we need to do a feasibility assessment. So one main question we have to answer is whether the patients in all trials match the target population for decision. And if they do, then all is fine and we can just proceed with the NMA. But if only a subset matches, then we need to ask ourselves whether there are reasons to think that there are differences in the treatment effect. If there are not, then fine, we can just proceed with the NMA. But if there are, then we need to think about how to deal with it. We could, for example, restrict the NMA to the relevant trial, so just exclude outlier studies. Or we could think about conducting a subgroup analysis if we have sufficient data, or meta-regression, but we need at least 10 studies per reporting on an outcome to do a meta-regression, which is also not always the case. Or we could use completely different approaches, such as MAIC or NMR, which Matthias and Nathan will talk about later today. Here you can see the networks we are usually dealing with. So in the upper left corner, you can see the ideal case of a large network of evidence incorporating a lot of studies for each link between the interventions. But I mean, this works well. Then if we have such a network, we can just use the standard code from the NICE DSU guidelines, and usually everything works well. But then if our network is rather sparse, like you can see in the upper right corner, where we only have a limited number of comparators and a limited number of studies informing the network, we have to think about alternative methods, for example, using informative priors or a frequentist approach such as Buho method or a frequentist fixed effects model, for example. Sometimes the network of evidence is also disconnected, like you can see in the right lower corner, where a study is disconnected, then MAIC would be a potential method which could be used to still compare the comparator of study 10 to our intervention. And also, of course, always we need to check whether any effect modifiers are relevant. Then also MAIC or NMR could account for these. Now I will show you a case study on choosing suitable priors in case of sparse networks of evidence. In the NICE TSU guidelines, non-informative priors on the between study standard deviation are suggested. These are usually uniform priors ranging between 0 and 5 or 0 and 2, and these work well in case of large networks of evidence when we have enough data to update these priors into the posteriors. But if we have only a sparse network of evidence, these do not work so well, and then there is still usually there's a large amount of uncertainty in the corresponding results. So one option to work around this situation is to use informative priors instead. And there's literature from Rhodes et al. And Turner et al. Presenting predictive distributions for continuous and binary outcome, or also for count outcome. The distributions can also be used for count outcome. And so they present these for a large variety of disease areas, from respiratory to oncology and many others, and also for comparison of pharmacological versus pharmacological interventions or other kind of interventions. So for most cases, you can find what you need in these tables they present in their appendices. And another option is to use weakly informative priors, such as half normal priors, for example. Then if you can already estimate the amount of heterogeneity in your analysis, if you think this might be a reasonable amount, you would choose a smaller value for tau. If you already know you have an extreme amount of heterogeneity, you would use a larger value for tau. So this is the example network of evidence I would like to show you. Basically, this is for a count outcome in respiratory disease. And so our intervention is the intervention X, which will be compared to a set of comparators. And even though the number of comparators is not extremely sparse, but the number of studies informing these is very low, with only one study per link in the network. And so we have used different priors to see how the results change and how sensitive the results are to the priors. So here you can see forest plots on an incidence rate ratio in respiratory disease comparing intervention X to a list of comparators. So if we use non-informative priors as described in the NICE DSU guidelines, as you can see in the upper left corner, we get extremely unrealistic results with an upper credible interval bound reaching up to 10.3 something, which is very unrealistic. Then if we use informative priors instead from Rhodes et al. From the literature, this would be an informative T prior, the upper credible interval bounds, they go down to 1.5, which is already much more realistic. And if we use half normal prior with tau of 0.15, we can see that the first time the decision reverses. So we can show for the comparison to comparator G that our intervention X is favorable over the comparator G because the 1 is no longer covered by the credible interval. But if we slightly increase the value for tau just to 0.16, then already the decision is reversed again. So if we look at these results, we can see they are extremely sensitive to the priors, and the DIC was also assessed, which is always similar between -5 and -7. So a decision according to the DIC could not be made as well. Here we have done a threshold analysis just to see how the decisions change if we change the values of tau for the half normal prior. So if we use a very small value of 0.11, we can show that intervention X does better than like 5 comparators, but if we increase it to 0.15, it's only for 1 comparator, and to 1.16, we can already see no difference anymore. So it's extremely sensitive. And of course, we cannot just choose the prior by just saying, okay, I like this result, so I use this prior. So we need justification for the prior selection. One possibility is always to use an informative prior from the literature following Turner et al. Or Rhodes et al. But if we decide to use a weakly informative half-normal, gamma, exponential, or any other prior, we need to justify our choice. So we could either look at the DIC, which in this case wouldn't help because the DIC values are very similar. So the DIC tells us something about the relative model fit, but for the absolute model fit to the data, we could conduct posterior predictive checks to make a decision. And so basically, if the model fits, then the replicated data generated under the model should look similar to the observed data. Basically, that means the observed data should look plausible under the posterior predictive distribution. And there are two main ways to do that. So either in a graphical way, we could provide data summaries on parameter inferences for if we have large data sets, for example, or we could show graphs of residuals or other measures of discrepancy between the model and the data. As an alternative, we could do numerical checks. For example, we could specify a test quantity and an appropriate predictive distribution. We could estimate p-values and say, for example, if the p-value was in a reasonable range between 0.05 and 0.95, then we could assume that the model fit to the data is okay. So that was all from my side. Matthias will now talk about matching adjusted indirect comparisons.
Yes, thank you very much, Katrin, and hello, everyone. So when we talk about non-standard situations in evidence synthesis and ITCs and also ways how to handle them, I think we also must talk about matching adjusted indirect comparisons, or MAICs. And I would like to give you an overview of this method in the next chapter of this webinar. So MICs or MAICs can indeed overcome some of the limitations of classical ITCs, and this is the case especially in the following situations. And you might remember the slide with the networks of networks we like and we don't like so much that Katrin has presented a couple of minutes ago. And there are especially two type of networks where MAICs can be of help. And the first situation is one where there is actually a network where there is a comparison where you see important effect modifiers. So for example, disease severity or age, and these effect modifiers would bias a normal indirect comparison of A versus B. And again, this has to do with the violation of the similarity assumption that Katrin has explained a couple of minutes ago. And the second situation where MAICs can be of help is if there are treatments of interest A and B, which actually cannot be connected through a common comparator. So the advantage really of MAICs now is that they can adjust for the effect of treatment effect modifiers in an unanchored comparison. But at the same time, MAICs can also remove some of the biases that you would typically encounter in an unadjusted or naive direct comparisons of outcomes when you don't have a common comparator. And this situation is again referred to in unanchored comparisons. In any case, if you do an MAIC, you need individual patient data from clinical trials for one treatment. And typically, this is, of course, the company's own treatment, whereas it is sufficient to have published aggregate data on baseline characteristics and also, of course, about the outcomes of interest for the comparator treatment. So before I go into the details of the method, I would like to sort of summarize in a visual way the key idea behind MAICs. And this idea is that you match the baseline characteristics from your study A, where you have patient level data, and you reweight them so that in the end they match on average the baseline characteristics from study B, where you only have aggregate published data. And then after matching, treatment outcomes are then compared actually across a more balanced trial population by using the weighted or adjusted means of outcomes from your trial A and comparing them to the observed or reported outcomes from trial B. So if we look at the actual steps to follow in an MAIC, I would say it's typically recommended that you compare the inclusion and exclusion criteria between your trial A and the comparator trial B as a first step. And there are indeed often situations where, for example, you have individuals with specific characteristics in your trial, and these individuals are shown here in yellow or purple on the left-hand side. And these individuals would not have met the inclusion criteria of the comparator trial B. For example, this trial B only enrolled individuals shown in blue, red, and gray. So ideally, before you do the actual MAIC, you should think about excluding such individuals from your analysis as a first step in order to improve balance. After this initial step, the actual MAIC approach can then be described through the following 4 steps or 4 elements. So regarding data collection, as I already mentioned, MAICs do need individual patient data for your treatment A, whereas you only need published aggregate data for treatment B. In terms of the matching criteria, it is typically recommended to select patient and disease characteristics that are known as effect modifiers and or prognostic variables. And I will say a few more words about these and situations when to distinguish this on the next slides. Regarding the actual matching, this is achieved by applying a weighting to patients receiving treatment A, so that after matching a weighting, they match the characteristics of patients receiving treatment B on average. And finally, after weighting, you would recalculate the outcomes for treatment A based on the weights you estimated, and you would compare these reweighted outcomes to the observed outcomes for treatment B, where you have the reported outcome data from a publication. So on the following slides, I would like to provide some more details and guidance for each of the steps we have just seen. And I would like to start with the matching criteria and the choice of matching criteria. And it is typically recommended that the variables to be matched or weighted on should be carefully considered and selected. Because if you include too many variables, then there is a risk that this will reduce precision, especially by reducing the effective sample size. On the other hand, if you fail to include relevant variables, relevant effect modifiers, then of course there is a risk of bias. Overall, the recommendation is that for anchored comparisons, that is where you have a common comparator arm, you should actually adjust for all effect modifiers, but not for purely prognostic variables. And this is in order to avoid over-adjustment and to avoid inflation of standard errors. Whereas for unanchored comparisons, the recommendation is really that all effect modifiers and prognostic variables should be considered. So to assess whether a variable is a potential effect modifier or a prognostic variable, you should ideally generate quantitative evidence. So for example, you could conduct a regression analysis with the outcome and see if any of the covariates is significantly associated with the outcome. But in addition to these quantitative analysis, you should also consider expert opinion, or ideally consider evidence that is synthesized by systematic literature reviews. And importantly, as always with non-randomized analysis, the recommendation is that you should conduct sensitivity analyses using different sets of matching variables. The core of the MAIC is now the actual matching. And as I already mentioned, this is accomplished by reweighting patients in your trial where you have patient level data by their odds of having been enrolled in the comparator trial. And for those of you who are familiar with covariate adjustments in different types of non-randomized studies, this approach is actually similar to propensity score weighting, and it is performed for all the selected matching criteria simultaneously. If you also have an anchored comparison, then you typically do the matching separately for the treatment arms and the placebo arms, and then it is possible to compare relative treatment effects, so for example, versus placebo between A and B. So in this example here, you can see that for a hypothetical study, you have a trial A where there are about 50% women and 50% men. So this is shown with the red bars in the left graph. Whereas for your trial B that you want to compare your results to, there are clearly more women than men. This is shown in the blue bars on the right-hand side. The matching then increases individual weights for females relative to weights, so that after matching, the distribution is the same as in trial B. And this is what you can see in the middle of the graphs. Finally, after matching, as I said, weighted outcomes can be calculated for any statistics for the outcome of interest. So for example, this can be mean rates or means in general. This can also be median survival, but it can even be a weighted Kaplan-Meier curve or overall. And ideally, you should also consider statistical methods that take into account the uncertainty around your estimated weights. Examples to use here are generalized estimation equations, and those take into account the uncertainty around the actual matching process. After matching, you can then calculate the effective sample size. And this is overall a measure that reflects sort of the impact of weighting on the sample size. And you will see that if the populations were balanced, each patient in the index trial would get a weight that is close to 1. And that means the effective sample size would actually be very similar to the original sample size. A low effective sample size, on the other hand, may occur when your populations differ substantially in one or more of the characteristics being matched. And this is then sort of the flip side of the coin, which comes along with correction for bias. There is also a technical support document, TSD, by the NICE Decision Support Unit, which makes recommendations about the use of MAICs, and I would briefly like to summarize them on this slide. So first of all, the document says that you should ideally only use unanchored comparisons when a connected network is not available. Secondly, the recommendation is that anchored comparisons must demonstrate that there are effect modifiers and that there is imbalance in these effect modifiers. So this is something that Katrin has already mentioned. And all effect modifiers, but no purely prognostic variables, should be matched in an anchored comparison. Regarding unanchored comparisons, the document suggests that you should ideally also include assessments of error that could be caused by unobserved confounding. And finally, there are also two more technical details that I want to mention. The first one is that indirect comparisons should always be carried out on the linear predictor scale, and you should always explicitly state the target population. So here I would like to present a small case study on the use of MAIC in ankylosing spondylitis, or AS. And this is a form of arthritis causing inflammation of the spinal joints and can lead to severe chronic pain and discomfort. The case study I'd like to present examined the relative effectiveness of secukinumab with that of adalimumab using matching-adjusted indirect comparisons in patients with active AS. And the outcomes considered were two binary outcomes, ASAS20 and ASAS40, and they measure improvements in several patient-relevant areas, including pain, function, and inflammation. So in this MAIC, outcomes between secukinumab and adalimumab were compared using patient-level data from the pooled Measure 1 and Measure 2 trials. That's what you can see on the left-hand side. And they were compared to aggregate data from the adalimumab ATLAS trial. And as is visualized on the top of this graphic here, there were indeed several differences in key baseline characteristics, including patient and disease characteristics, which would have led to an imbalanced comparison. And as a result of the MAIC, the effective sample size in the Measure 1 and Measure 2 trials have then dropped from 197 to 120, but obviously the matching then resulted in some more balanced comparisons. As you can see on this slide here, there were several differences, as I said, in key patient and disease characteristics before matching. And this included inflammation parameters such as CRP, included measures of function such as the BAS-FI score, but also included different distributions of age, sex, and prior use of therapy. So this is what you can see when you look at the blue and the gray bars. So the blue bar shows what you can see when you look at the gray bars and the brown bars. So the gray bars show the outcomes in the measure trials before matching, and they are different from the brown bars for the ATLAS trial. Whereas after matching, and this is what you can see by comparing the blue bars with the brown bars, all the characteristics considered in the matching were then identical after matching, identical with the average distribution in the ATLAS trial. The nice feature in this case study was actually that both anchored and unanchored comparisons were performed. So placebo-adjusted or anchored comparisons were actually feasible at early time points at week 8 and week 12. So anchored MAICs were performed at these early time points. And as you can see here, these MAICs, these anchored MAICs, showed that there was actually no evidence that ASAS20 or ASAS40 responses differed significantly between the secukinumab and adalimumab arms at week 12 or 8. As the unbiased placebo phase in these trials actually ended at week 12, comparisons at later time points, that is at week 16 and week 24, were unanchored. And the results of this unanchored comparison shows that there was weak evidence that ASAS20 responses were higher with secukinumab than adalimumab at week 16. And similarly, at week 24, there was up to moderate evidence that ASAS20 and ASAS40 responses were higher with secukinumab. So if you want to take a closer look to this case study, you will actually also find the full text publication of these analyses among the articles for download. So to summarize, I would say that MAIC is actually a method that enables you to adjust for confounding in unanchored comparisons, as well as address effect modifiers in anchored comparisons. But there's also a further, even more recent method to address effect modifying in evidence synthesis, and this is multi-level network meta-regression. And I will now like to hand over to Nathan, who will present this method in more detail.
Okay, great. Thanks, Matthias. Yeah, so I'm going to talk about ML NMR for the next 10 minutes or so. So we've just seen the MAIC as a method for population-adjusted indirect comparison using IPD in order to address bias. Now, the gold standard situation for this, the ideal situation is if we had IPD for all of the studies so that we could fully adjust for patient differences using network meta-regression, which is really just regression. So obviously we don't have this. This is the real world. So we often only have IPD for our own studies, for one of the studies. So if this is the case, we can still use the IPD to try and adjust differences in the covariates between populations. That's what we've just heard about with MAIC. So why can't we always use that? So some of the issues with using MAIC are that it's actually it can only really be used in a limited fashion. So it estimates relative treatment effects between pairs of trials, where we have IPD for one of the trials and we have aggregate data for another trial. So we've kind of got this two-study direct comparison. So this causes issues for larger networks and as networks grow. The MAIC as currently proposed is also unable to achieve estimates in a population other than that of the aggregate study. So it's limited in that respect. In particular, it may not be the actual target study of interest, so the target population of interest. So it may differ from the target population of routine clinical practice in a particular jurisdiction, for example. So this is kind of a second issue. Finally, well, these are the three issues basically. So the first point that needs to be addressed is that we can synthesize to larger treatment networks. The target population really should be arbitrary, and we should have flexibility of that, not constrained by the aggregate study. And we still want to be able to avoid aggregation bias, things such as the ecological fallacy, which you may well be aware of. So my proposal, or rather Filippo's proposal, which I'm going to discuss, is the ML-NMR method for addressing these as an extension and a generalization of the NMA framework, and as a alternative to the MAIC. I realize the ML NMR is not such a catchy name. Sometimes it's called the Filippo method. Filippo is the original author who coined this acronym, and one of his key papers is there at the bottom for reference. It's in contrast to these previous approaches where we often plug in mean covariate values to the IPD models. Instead, the ML-NMR method embeds a probabilistic approach to population adjustments within the aggregate NMA model. It essentially consists of two steps here on the right-hand side of the slide. So the first is to define an individual level regression model on the IPD. And then the second is to average, or in this case, integrate over the aggregate study population to form an aggregate level model. So we're kind of using the aggregate level inputs via the IPD regression. Now, in the next couple of slides, or next few slides, I'm going to try and explain exactly what that is with some simple graphics. And hopefully this will get across some of the intuition. I'm going to be using some dummy data, and this is necessarily simplified. So this is not a kind of a direct application, if you like, but it does contain the core components of the method. So imagine that this is the IPD study. So on the x-axis here, this could be age, some continuous value, and on the y-axis, some outcome, for example, blood pressure. And then we can, because we've got the IPD, we can fit a regression to give us a relationship between the two. If we were to, for example, if we had a counterfactual situation, and so this line is for one treatment. If we gave these same patients another treatment and we had a shifted line, the difference between these two lines could be, the idea of that is this would be some kind of relative treatment effect. So let's extend this then, because what we're actually interested in is, imagine that there's a second study for which we only have aggregate data, and that's what I've tried to represent here. So our aggregate data now is going to be the stuff in red, and the IPD is going to be the stuff in blue. So we've still got this IPD, the points of the IPD and the regression fit, but now I'm showing the aggregate data. The aggregate data originated from the IPD. We just don't have access to that. But I've actually shown the red points on the plot anyway. But we actually only have access to the summary statistics. So in that case, that would be represented by these histograms on the x-axis and the y-axis. We can see that the distribution on the covariates is imbalanced between studies because these histograms are different at the top. And we can also see the relationship between these and the outcomes are different because we can see the difference in the location and the gradient of the fitted line. So these studies are telling us a different story, and we somehow want to combine this information. So the aggregate data study only provides summary statistics, like I just said, for example, a mean and standard deviation. So we could just plug in the mean into our IPD regression to get a value for the outcome. And this is shown here with the horizontal blue dashed line. So here we've got the vertical red dashed line, which then meets the solid blue line, so that's our fitted IPD regression, and then we get our kind of prediction of that as this dashed blue line. And we can do the same thing for the standard deviation and some kind of spread, which I've shown here with these transparent color blocks. So we can see how we can use the aggregate data values as inputs and kind of filter that through the IPD regression to estimate some outcome values. problem with this is that it doesn't correspond to the average outcome that's also provided in the aggregate data study. And this is indicated by the dashed horizontal red line, as you can see below. What the ML-NMR does, cleverly does, is it comes up with a relationship between the input covariates and the outcome, which incorporates the information from both the IPD and the aggregate data. So that is, it uses the blue points, the IPD, and the red histograms, which we've created from the summary data, together. So this results in some regression fit line here, which is a compromise in terms of the location and the gradient between the two studies. Because we don't have IPD for the aggregate data study, we use a distribution of these input covariates, the histogram at the top, and we integrate over it to estimate this aggregate data study outcome via the regression, like I said. So there is a step where we need to make some assumptions of the actual distribution of the covariates given the summary statistics. So an obvious example is if we were given a mean and standard deviation is to assume a normal distribution. And this is what it looks like in formulae. So the left-hand side is the individual level data model, submodel, and the right-hand side is the aggregate data submodel. And you can see here that point 2 here is where we integrate over the regression, and the regression here is linked function g, and that g is you can also see in the regression on the left-hand side. So these are two linked sets of equations here, linking the aggregate and the individual via this integration. Just to say that this integration totally dependent on the model setup. It can be a simple and straightforward step, or it actually can be rather non-trivial depending on the correlation and the particular distributions of the covariates in the model. So that sounds great, but this isn't the end of the story. This is a relatively new approach, and this is an active area of research, and there's still some important open questions. These include, how does this apply to disconnected networks or unanchored scenarios that Matt has talked about? It's still open research on how to apply this to survival data. And there's an ongoing statistical issue you hear about at conferences about which is better, a conditional treatment effect as opposed to a marginal. And also, how do we standardize? Well, these are more technical issues. So this does sound, it sounds to me, it sounds very powerful. It is arguably one of the more sophisticated approaches for NMA. But fortunately, someone else has already done the hard work of implementing these methods into software tools. And this multi-NMA package is written in R, and the author is Filippo, who's the original author of this method, and whose reference I gave you on the previous slide. So I'm just going to show you a very simple example of using this package to do a ML-NMR. So there's really only 3 steps. So first of all, you have to specify your IPD and your aggregate level data, which I show here on the left-hand side, which is as simple as saying what your sample sizes are and how many successes or fails there are, for example, depending on the type of data. And then you also have to specify this integration, this add integration function. So you need to say how as I mentioned when we were looking at the plots, you need to say how you're distributing your input covariates. So this is essentially specifying distributions. Here we have gamma, Bernoulli, and etc., specifying distributions for your covariates. And then finally, it's as simple as running this NMA function to do the full analysis. And behind the scenes, all of the calculations are handled for you. Because this is done in a Bayesian paradigm, we also need to specify prior distributions for all of the analyses and all of the issues that go around that. And here's just an example of some of the output. Points of note here, as you can see, the posterior distributions for the different coefficients, the prognostic and the event modifier, and you can also see the relative effects here. So I'd just like to finish by kind of explicitly making a direct comparison between the MAIC and the MLR. So the MAIC can introduce bias in some cases. It's only applicable for 2 studies, and it's limited in terms of the target population, where the ML-NMR is much more generalizable. On the contrast, the MAIC is much more well established. It can handle unanchored networks, and it's been used in survival analysis. So in summary, we've looked at handling sparse data, heterogeneity, and disconnected studies. For the sparse networks, we've looked at how to incorporate informative priors to deal with that. We've looked at using the MAIC and the ML-NMR in order to use IPD data to address issues with bias, and some of the pros and cons of using those two. So with that, I've wrapped up. So I think I hand over to Sydney now.
Okay, first question is, can we do MAIC with RCT comparing with RWE study? What are the risks in this comparison?
Okay, I think this is for me. I think the simple answer is yes. We can also do MAICs with RCT data, comparing them to data from our real-world evidence study. And yes, I think there are additional risks in such a comparison, but it doesn't mean that you cannot do them. And I think among the risks are obviously the ones that you always have when you compare data from a more controlled environment, such in a randomized controlled study, to real-world data. So I think there are some questions you would have to consider, such as, are your outcomes really comparable? Have they been assessed in the same way and at the same schedule? So, for example, in oncology, progression is often not really comparable because it's done with strict RECIST criteria in a trial, but often you only have some sort of real-world progression in the real-world study. And of course, I think you should also pay more attention on making sure that, the populations are comparable, and maybe make sure that the inclusion and exclusion criteria are similar, and maybe adjust them if possible. Especially, I think this situation isn't that rare, because often you might have, or there are situations where you have a single arm study for a rare disease and you don't have a comparator in your study, and often the only good population for comparisons is evidence from an external or historical control. And I think even such an unanchored comparison versus historical data, MAICs, can be used. And we have done such analysis actually, and HTA agencies do consider and even accept such evidence if you can show that this is really still the best evidence that you can provide.